Welcome to 2020, where almost everything is connected. In few years, global, national, and regional networks will connect trillions of wireless devices. Even at home, hundreds of objects will be connected and will send and receive hundreds of messages. Proudly, the Internet of Things will connect the world. My name is MariaSarkis, third year telecommunications engineering student at UZAC. In this presentation, I'll be talking about long-range wide area network, also known as LoRaWAN, how it works, what are its different end node classes, we'll go through a small introduction to chirp spectrum, and finally, we'll talk about the importance of LoRaWAN and Internet of Things. Sometimes people think that LoRa and LoRaWAN means the same thing, but there's a small difference between them. So let's go through a small introduction to each term. LoRaWAN defines the communication protocol and system architecture for the network, while LoRa is the physical layer which enables the long-range communication link. And here what do we mean by long range is distances up to more than 20 kilometers. LoRaWAN also is responsible of joining different LoRa devices, managing their channels and connection parameters like bitrate, bandwidth, spreading factor, etc. The way LoRaWAN protocol works is fairly simple because we can compare it to professor and students in a lecture. The professor or the gateway can speak to end nodes that are the students here and vice versa. And everyone in the class could be trying to communicate with the professor at the same time. But surely the professor wouldn't be able to hear or understand them all at once. Here's what that looks like in practice. The node that is in general a sensor transmits into the radio spectrum blindly, and any gateway lucky enough to hear the transmission can take it and send it up to the cloud. So as the data packets from the end devices enter the circuitry of the gateway, it comes in chirps, then parsed down to the frequency domain, and then a modulated signal to efficient data transport. Note here that it's possible that all the gateways might hear the message and send it. And here's an advantage, because message can still be transmitted despite very weak links. Now once a message has been delivered, there is no acknowledgement received. However, nodes in LoRaWAN can still request acknowledgement. In this case, if all gateways pick up the same message, the cloud chooses only one gateway to respond at a fixed time. So here we may sometimes face a problem because when that gateway is transmitting back to the node, it stops listening to everything else. So if the application needs lots of acknowledgements, it will spend more time transmitting acknowledgement, which may lead to network collapses. Let's now talk a bit about LoRaWAN end nodes. LoRaWAN has three different classes of end devices to address the different needs reflected in the wide range of applications. These three classes are Class A or bidirectional end devices, Class B or bidirectional end devices with scheduled receive slots, and Class C or bidirectional end devices with maximal receive slots. So let's begin by Class A. Class A is purely asynchronous, which we call a pure aloha system. What that means? This means that the end nodes don't wait for a particular time to speak to the gateway. They simply transmit whenever they need to and lie dormant until then. So if you have a perfectly coordinated system over 8 channels, for example, you could fill every time slot with a message. As soon as one node completes a transmission, another starts immediately. Now for Class B, end devices are also bidirectional, but here with scheduled receive slots. So in addition to the Class A random receive windows, Class B devices open an extra receive window at scheduled time. In order to do so, and for the end device to open its receive window at the scheduled time, it receives a time synchronized beacon from the gateway. This allows the server to know when the end device is listening. Note here that Class B and Class C devices must also support Class A functionality, but a Class B does not support device C functionality. Now we conclude this part with class C, where devices are bidirectional with maximal receive slots. What do we mean by that? These devices have continuously open receive windows which are only closed when transmitting. This allows for low latency communications, but is actually many times more energy consuming than devices in other classes. This is used primarily for AC powered applications because it takes a lot of energy to keep a node actively awake, running the receiver at all times. Earlier in this presentation, I mentioned the word chirp. What do we mean actually by chirp and chirp spread spectrum? So let's see. First, LoRa end nodes and gateways are transceivers, since the communication between them is bidirectional. So LoRa end node can send and can receive data from the gateway, and same thing for the gateway. So, as already mentioned, LoRa is a proprietary spread spectrum modulation scheme that is based on chirp spread spectrum modulation, or simply CSS. CSS is a technique that uses wideband linear frequency modulated chirp pulses to encode information. A chirp is often called a sweep signal. It's a tone in which the frequency increases or decreases. When it increases, we call it an up chirp, and when it decreases, we call it a down chirp. And these chirp signals are used as carrier signals where a message is encoded on. Here's a figure showing us the both cases. For the up chirp case, remark that the signal, when it starts from the lower frequency and increases up to the higher frequency. Once it reaches the highest frequency, it gets back to the lower frequency, then increases again to the higher frequency, and so on. That's the same logic for the down chirp, where the signal starts from the higher frequency and decreases to reach the lower frequency. Once reaching this stage, it gets back to the higher frequency and decreases again until the lower frequency, and so on. So to generate chirps, the modem modulates the phase of an oscillator. The number of times per second that the modem adjusts the phase is called the chip rate and defines the modulation rate. And here's a figure showing us two different cases. The first one is when the signal is unmodulated, and the second one after modulation. You might have wondered why I started my presentation with the Internet of Things, while actually my presentation was all about LoRa, LoRaWAN protocols, networks, and so on. So here's the answer. LoRa technology has restructured Internet of Things by enabling data communication over a long range while using very little power. Internet of Things is nothing more than sensors sending small packets over the internet. So with this operation to be done, it won't require a higher bandwidth, but it will need a high range. So clearly, these requirements are provided by LoRaWAN. And as we can see in this small illustration, it shows us the difference between LoRa and cellular and Wi-Fi or BLE in terms of bandwidth and range. To sum up this discussion, we can say that LoRa devices accommodate a vast range of Internet of Things applications by transmitting packets with important informations. LoRaWAN also fills the technology gap of cellular and Wi-Fi based networks that require either high bandwidth or high power or have a limited range of inability to penetrate deep indoor events. And finally, and the most important part, is that LoRaWAN has significant cost savings in the deployment and required infrastructure compared to existing systems. That's all. Thank you for your attention. I hope that this presentation added some new information to your knowledge.